these systems in the end would be working on a blockchain. So that's the thing. We are working on a blockchain that enables a decentralized asset motivation in which the assets, the EV chargers, the photovoltaics, the other aspects of energy, they are decentralized. They are working on a decentralized method so that it could be more feasibility could be achieved over that. Second one is EV charges, and third one is renewable systems. So these are the three aspects in which ChargeMOD as a company works on. Right. So like I said, environmental aspects are some of the prime things that any young guy or any young person is currently very empathetic about, right? Our future generations might not be much aware of that because they were not aware of the consequences that environmental concerns could bring in, that pollution could bring in, right? It's not their fault. They were having a phased relation, right? So it's all phases. So we are coming in from phases, phase 1, phase 2. We had the IC engine phase, which led to multiple developments in the IC engine sphere. We are now having this EV phase, which will help us, which will enable us to go through the other phase, which will help us, gain more independence from the from the gasoline fuels, and maybe help humanity lead a little bit more affluent life, right? So that's what the whole idea is behind having a good earth, having a good world that is free of emissions, right? So with ChargeMOD, we actually work with many major companies like Tata, the Mahindras, the SVM, Srivaru, and we are in discussion with many other majors. We work directly with them for providing charging infrastructure related equipments, charging hardware, charging software. We're also in discussion and in provision of charging solutions, charging software solutions for a wide range of customers throughout India. So basically, our competence with ChargeMOD is where we provide an assimilated portfolio of hardware and software so that things for the end customer becomes very easy. And that's what ChargeMOD does, right? In the simplest terms. So a partnership, being a startup from Kerala, being a startup from kozhikode in Kerala, having a scope of achieving something good, something that is interesting, is giving us very pleasure, and letting ChargeMOD having this presentation in front of you guys is also something that is very interesting and very proud for us. All right. I think, sir, I'm very clear on what ChargeMOD does on a very basic level. And
yes,
Ramanunni. So now we shall move into the
yes.
Yeah, got it. So last time when we had the discussion, I think we had a discussion on how charging schemas works, what are the different charging schemas, how charging is enabled between different participants, how charging is enabled between different schemas, right? We also understood what are the protocols, what are the common paradigms that are available for charging. Now, when you come into the new era of mobility, when you come into the new generation of mobility, you're going to see a convergence of different technologies. You're going to see different technologies or different separate different domains that were separated in the past coming together, right? So, like I said, an automobile factory was never considered a software or a higher-end techno manufacturing facility, right? But consider this, every single electric car that Tesla makes is actually a robot. Simple as that. Every single vehicle that Tesla makes is a robot. Every single vehicle that most of the major electric vehicle manufacturers make is a robot. Most of them have self-driving facilities. Most of them has cognizant accident recognition facilities. Each of them are having their own specifics that are related and that are converging, right? So in the future, we might be seeing multiple, energy distribution methods, right? It could be vehicle to vehicle. When mobile phones, power banks, all this came, we had a discussion on charging from mobile to mobile. Even though it took a long time, we do have that right now. We can use your Samsungs like S21 to charge another phone, right? So that is there. You can charge a mobile phone from another mobile phone. It's a similar thing. It's in concept. It's nowhere near. So vehicle to vehicle is a concept in which, a vehicle which is driving close to you, one of the vehicles might be having a higher potential. The other vehicle might be at a lower potential. So they must be able to transfer the energy within a close contact range through an inductive method or through a contactless method, right? And that's one thing that is very interesting. That is very interesting to imagine. That is very interesting to see in pictures. But when it comes to real life, I don't know how far that companies have achieved these aspects, right? Second one is vehicle to devices. This is something that has already been achieved, in which the vehicle, the battery electric vehicle, is used as energy storage system, ESS. And this ESS, or this energy storage system, or the electric vehicle, is used then to power another application devices. Right? Maybe when you are going out tenting, you want to have electric induction cooktop that needs to be worked. So you can do that. You can connect to your electric induction cooktop to your vehicle, draw the power, right? So that's something possible. The third one is vehicle to infrastructure. So this is the case in which the vehicle, the electric vehicle, is giving back energy to infrastructure. So vehicle to infrastructure and vehicle to grid, how do they differ? Is vehicle to grid is directly in convergence with the whole grid schema. Vehicle to individual infrastructure could not be or may not be in harmony with the whole grid. So that's the whole interest. So vehicle to infrastructure is kind of like a subset of vehicle to grid. That's the case, right? So these are kind of like how we see the thing. Vehicle to grid, that's the final and that's the most important aspect, right? Electric vehicles are obviously energy storage systems. They have huge battery packs. They, when in together in number, or when in huge production, you're going to see huge amount of energy storage systems driving through the runway. So the question is, why can't we use these energy storage systems as a generator to modulate the peak value conditions, to modulate any demand that occurs, to modulate any dips that occur in the grid, right? So that is the condition behind, or that is the thought process behind vehicle to grid infrastructure. So vehicle to grid is a simple yet complicated schema in which the vehicle acts as the generator for the grid, in which the vehicle, normally while charging, the vehicle gets the power from the grid, charges the vehicle, right? So it happens the other way, vehicle to grid. And there is something in the vehicle to infrastructure, you can have the vehicle to home schema. Vehicle to home is very simple. It's similar to vehicle to grid or vehicle to infrastructure, except that it powers the entire home. Like the Ford F-150 Lightning, the newest vehicle from Ford, I think it could completely power your home for 8 hours. Completely power a modest American home, which could be on the higher side in terms of energy utilization, an American home, average American home, for 8 hours. That is something that is pretty interesting, right? So that is the new generation of charging, or new generation of inter-energy transaction that we are seeing in the future. So this I've already mentioned in the last presentation, like what are the charging methods that we have. We have got conductive methods in which we plug in the wire. So we've got inductive methods in which we have a wireless power transfer that is happening, concept method, and battery swapping. Battery swapping is a way in which you replace the battery, like how you do in your remotes. When your battery is dead, you replace that. But it's a little bit more complicated because obviously each and every vehicle has, like I said, each and every vehicle has a different battery capacity and things like that. So that is a little bit complicated, like I said, but still researches are going on down the sphere. So basically, when you charge using an AC charger, like I said on the last presentation, you get the electricity from your grid. You make it go through the onboard converter, convert it into DC, and charge the lithium-ion battery. And when you're fast charging through DC charging, you bypass the onboard charger. You directly connect to the BMS. BMS is which obviously is the battery management system, like I mentioned in the last session. A battery management system is in charge of controlling and monitoring all the activities that are going on, that are present, or that are happening within the battery, within each and every cell. So the battery management system is actually an electronically controlled programmed schema, which does all the thing, right? And the modes of charging, I'm just refreshing the whole thing so that we could go into more technical stuff. So levels of charging I mentioned. Level 1 could be 230 volt at 15 amp, delivering a max power of 3.3 kilowatt. Level 2 is the same schema in which AC power is provided to vehicles at a power that is higher than 3.3 kilowatt. It can vary from 3.3 to 22 kilowatt, which means that in turn at level 2 we can give AC currents from 15 amp to 18 amps, right? So this can reduce the charging time very drastically. Level 1 and level 2, there is a complete difference between the charging time. For example, the Hyundai Kona on a level 1 charger or on your normal home charger, it would take around 21 hours, 19 to 21 hours to full charge. But on a level 2 charger, it takes close to 6 hours. I think it takes close to 5.5 hours for a full charge. So that is the difference that the level 2 chargers bring in, right? And the level 3 is the DC charger, in which the AC-DC conversion happens off the car, off board the car, and the whole thing is controlled through a specific charging protocol. The CCS, which I asked you to be very specific about, which I was more specific about because CCS is the charging schema that is more prevalent in all part of the world. Like last said, there are multiple pins that are available for connecting your electric vehicle. These are the types of pins that are available: the CCF, the ChargeMOD, the Bharat EVSE, the GB bar T, etc. And on the far right side, you can see the CCS2, which is kind of like the global norm that manufacturers are following, or which is kind of like the harmonized or unified charging plug that manufacturers are using right now, right? So the rest of our discussion, or the rest of the whole discussion, would be revolving around CCS2, the protocol behind it, the communication layer that is behind it, how does the vehicle communicate with the charger and everything. So we are going to look into that practically, and basically we are going to make an EV charger. So that's what we are going to do. We are going to do through this session. We are going to make a level 2 AC charger, which has a communication with the electric vehicle and the electric vehicle charger. So if you guys are with me, we will be able to make an electric vehicle charger by the end of this session. All right. So why do we need an electric vehicle supply equipment? That is a question. Why is it required first place, right? You can just directly plug in AC, right? Why does even the charger or the AC device is required? So basically, this is required on the primary side for in the terms of a safety purpose. So the electric vehicle supply equipments are a safety equipment consideration. This is kind of like a safety equipment consideration. So basically, as you can see from the document, the power pins of the vehicle or of the EVSE or of the charger will not be powered until the EVSE and electric vehicle, or the EVSE means the charger and the vehicle. EV is electric vehicle, and the charger and electric vehicles negotiation is complete. I'll get into that. I'll get into that in very detail. So that's something that is very important, right? You don't want the endpoints to be powered because you're handling it with your hand. It's 16 amps, 3.3 kilowatt, or it could be 7 kilowatt, which is pretty hazardous. It could be deadly, right? So you don't want that to happen. That's why you have a control ecosystem to charge the vehicle. And plus, you do not need any kind of interruptions. You do not want your child to put your hand into your finger into the socket and something bad to happen. That there is a chance for that to happen. You don't want that to happen. The companies don't want that to happen. That's why we have the specified protocol or specified systematized, standardized EVSE systems that are available in the market, that are produced by major manufacturers, including us, for safety charging of electric vehicles. Now, second part, as you can see, the ground fault circuit interrupt. So basically, the ground schema is very important for EVSEs because as you might know, there is a communication involved that involves power line communication. But if you do not have a proper ground detected, then obviously the systems and the signals could behave very wacky, right? The systems could give you values that you are not expecting. The systems could give you, it could start, stop. It won't completely work in the way that you want it to be. So if your ground is not correct, it's going to be pretty wacky. So what happens is that on the initial connection checkup, the earth wire is completely checked, the earth system is completely checked, earth leakage is completely checked, so that we have a clear environment for charging the schema. The next point is graceful startup or shutdown, which means that, like I said, you want the electric vehicle to be started up or to be shut down at the point when you want it to be, because you're handling high powers. You don't want any relays or contactors to be opened or closed at high powers. See, when you're handling 7 kilowatt, you don't want an abrupt opening of a relay. You don't want an abrupt closing of a relay. You don't want an abrupt pulling in your charger. See, these are all dangerous conditions. These could lead to welding between the relays. This could lead to welding between the contacts of the contactor if you're using a contactor. This could lead to the welding or shorting between the pins of the electric vehicle charger. It could lead to the lessening the life of the electric vehicle charger. So these are aspects that play right in the ground verification schema. Plus, like I said, if the ground is not correct, the signal values will be wacky, will be not correct. It will give you, like you said, it's a truth table kind of a scene. It's similar to a truth table value that we'll get into later. So if you want the signals to be perfect, if you want the signals to be exactly what you want, you need the ground to be perfect, you need the ground to be verified and checked to the constant, right? And next we come to the pilot signal, which I'll get into. So pilot signal is something, I'll show you something. So this is an electric vehicle charger connector. You can see 5 pins in here. 1, 2, 1, 2, 3, 1, 2, right? So the top first 2 pins, these are the pilot pins. The first pin is the control pilot and the second pin is the proximity pilot. The control pilot line carries the data signal or the square wave signal or the pulse width modulated signal that carries the data, that carries the negotiation value through the EV and EVSE, right? And the other one, the proximity sensor, is in place, the next small pin on the top, right? That is present to confirm whether an EV has been properly connected within the vehicle ecosystem and has been properly latched and locked. So that is the purpose of the second pin, the proximity pin. Other than that, you can see 3 plus 2, right? That is L1, L2, L3, neutral and earth. So these are the whole pin layout. I'll give you a little bit more distributed schema. So just keep it in your mind. You've got 2 pilot pins. One is the control pilot, which carries the data signal, and the other one is proximity pilot, which carries or which identifies whether the charger has been connected, latched properly or not, right? Just keep that in mind. So yes, so this is why, like I said, electric vehicle supply equipment is required. And in this session, we will be keeping the J1772 overview or J1772 protocol in our mind, and we will be following the J1772 protocol, which is a Society of Automobile Engineers recommended practice. As you might know, SE does all of the automotive kind of regulations in the North American market, and J1772, the practical aspects of it is very similar to the CCS schema, which I have shown you, right? So basically it's the same. So I recommend that J1772 would be the initial easiest way to have a representation or have an understanding of how the charging happens between a vehicle and an electric vehicle charging station, right? So I'll just consider and I'll just give you a little bit of glimpse into the J1772 classes. It's similar to what I've described before, the level 1, level 2, and level 3. Level 3 is DC, level 1 is AC, which has a maximum of 16 amps to 3.3 kilowatt. 1.9 is the median power, 3.3 kilowatt is the max power. Level 2 is at 240 volt. It can be from 1 phase to 3 phase at 415 volt AC. The max current could be at 20 kilowatts, right, at 80 amps, right? It could be up to 22 kilowatts. At max, right? And DC, depending on the voltage, depending on the current, you could have the variation from 80 amps to 200 amps, right? So basically, you can vary your power on DC between 15, 10 kW to all the way up to 100 kW and even above that. There are systems that are capable of delivering at 1000 volt DC and maybe up to 250 kW, right? So DC is capable of delivering at higher power, while level 1 and level 2 are capable of providing powers, and level 2 is capable of providing a higher power at AC, right? So this is the J1772 schema. So J1772 is the basic premise, or like the basic protocol that has been behind the development of AC signals, right? And now we'll be using some terminology which, as in terms of electronics, electrical, you should be familiar with. We should be using a 1 kilohertz pilot signal to communicate the EVSE and EV state, right? That, like I said, there are 2 pins, the control pilot and proximity pilot. And through the control pilot, we will be having this 1 kilohertz pilot to communicate between EVSE and EV. And the duty cycle of the pilot signal or the 1 kilohertz wave determines the maximum current that is available to the electric vehicle. So the duty cycle of the wave is what that, just keep these in mind. Just keep these in mind. We'll come into these very in detail very shortly. The duty cycle of the pulse width modulated wave, the 1 kilohertz square wave plus or minus 12 volt, determines the maximum current that is available to the electric vehicle. And the proximity sensor, like I said, it is what actually controls and checks whether the vehicle has been completely latched, securely connected to the vehicle, right? So I think you should be familiar with something called the state machine, right? So State machine, as I think you must be knowing about it, or I'll just explain it in a very simplest term. A state machine is something, or a schema, or a mechanism which behaves in a specific way at different states. So you have your system behavior in a way at state 1, in another way at state 2, in a completely different way than state 1 and state 2 at state 3, right? So you'll be having the the corresponding values and the corresponding action for that, right? For the state machine. Or you can consider it as a truth table, even though it's not an exact truth table, right? It's not a truth table, right? But you can consider it as a truth table, right? If required. So I know this, by seeing this, it could be pretty confusing. It can lead to a lot of confusion, like what these states will understand and what these states will carry, right? So I'll show you a basic circuitry representation of how electric vehicles and electric vehicle charging stations interact. I'll just show you that. I hope the screen is visible. So the thing is, on the left hand side, you have the EVSE connector. This whole side, this is the EVSE side, left side. LHS is EVSE, and the RHS is the vehicle side. So you have the vehicle, you have the EV charger, you have the vehicle. These things are mated together, right? So this is the very basic representation of how an electric vehicle is connected to an electric vehicle charging device, right? So first consider this signal, the pilot signal, the number 4 signal. The number 4 signal at pilot. So the number 4 signal at pilot, when consider this J1 and P1, the female and male, they are connected together. And when they are connected together, you could see that there is a 12-volt line that is coming in through the straight line, through this line, and this is a voltage detector. This is a voltage detector, a voltage comparator. So this 12-volt line comes in. So basically, when the vehicle is not connected, this line should give you 12 volts, right? But when the vehicle is connected, what happens is that this switch, as you might see, it gets latched. When it gets latched, what happens is that then the 12-volt DC signal, it gets converted into a 12-volt plus or minus 12-volt 1 kilohertz square wave supply. I think you must be understanding. So when the vehicle is not connected, you will be having 12-volt on the line. So what happens is this detector, this detector or this voltage comparator is designed in such a way that it detects any drop below 9 volts. So what happens is that the 12-volt signal is something that is pertaining here, and when the vehicle is connected, this whole thing falls in through this latch is connected, and the whole line is powered through by a plus or minus 12-volt pulse width modulated square wave with a 1 kilohertz frequency. So that is what happens when the vehicle is connected. And thus, when the vehicle is connected, as you might see, this D1 is a diode that is present to do a diode check. This diode is present to avoid any kind of accidental power surges, or in case your connector falls into a puddle of water and that water has somehow has an exact resistance of what the system provides, and it could somehow energize. It could be a 1 in a million chance or 1 in 10,000 chance, but still it's a chance. That's why you have a diode there, which does a diode check to ensure that the system that is connected is the vehicle indeed, right? So the presence of diode is just that. Just keep that in mind. And now, when the vehicle is connected, as you might see, the whole 12-volt supply goes in through this line and it drops across R3. The voltage drops across R3, the third resistor, which is a 2.74K resistor. So when the voltage drops across R3, what happens is that the voltage gets dropped to 6 volts. No, 9 volts. The voltage gets dropped to 9 volts. As you might know from the voltage division that is happening there, the voltage gets dropped to 9 volts. And when that happens, the voltage detector here, comparator here, understand the voltage in this line has been dropped to 9 volts, and it understands in such a way that the vehicle has been connected. And thus it connects directly to the controller, which is a microcontroller that is programming and that is getting the values. And it could be an Arduino, it could be any of the microcontrollers that are available in the market that could do the whole thing, right? The microcontroller must be paired with multiple voltage comparators that could help us do the thing, right? And when that happens, when that 9-volt signal is given in, right? So this part of is energized. This part is into consideration. And then when that 6-volt is considered and this square wave is then aptituded and then changed to a specified pulse, specified duty cycle. Like I said, the duty cycle of this pulse width modulated wave gives you the power, gives you the maximum amperage. As you might know, the voltage remains constant at 220 volt. So the only way you can change the power is by changing the current. And thus the current of this system of this availability of this system is determined or is controlled through the duty cycle of this system. Right. So when you give the duty cycle at the required rate, and after it has dropped in through and it has got a connection schema, the voltage has been dropped to 9 volt, which means that the vehicle has been connected. Now, this switch, as you can see, this is the switch on the vehicle side. This is on the vehicle side. What it does is that this switch is actually responsible for unplugging and connecting when the battery is fully charged or discharged. Right. So if the battery is charged, then obviously the switch will be open. If the battery requires charging, then the switch will be closed. And if that switch is closed, then the voltage runs in through further 1.3K resistance and the voltage drops to 6 volts. So now when this switch is latched, as in when the electric vehicle gives in the permission to charge, this voltage, this relay is latched, this switch is latched, and the voltage drops in across R2. And the effective voltage becomes somewhere around 880, and thus the voltage on the line becomes 6 volt, right? So consider this in mind, consider what I've said in mind. Now we'll take a look at the truth table. So I think it could be a little bit more understanding right now before than when you first saw. Right? So first state, when your electric vehicle is not connected, you'll be having the 12 volt on the pilot supply, right? But when the electric vehicle is connected, the voltage is dropped across this 2.74K resistor, and thus the voltage is dropped to 9 volt. I'll show you that. Like you see, when this pilot line is connected, the voltage is dropped across R3 at 2.74K resistor, which lowers the value, which lowers the voltage drop, which drops the voltage to 9 volt. So 9 volt is the state B of the machine, which gives us the option, or which gives us the assumption that the EV is connected, ready, but not charging, right? And at this point, as you might see, the frequency that earlier it was a basic DC line, and now when it is connected, we'll switch to the square wave, the pulse width modulated wave, which has a frequency of 1000 hertz, and which will give the through which we will give the duty cycle, which gives the amperage. I know it could be a little bit confusing, but I think this could be the easiest way that I could be representing this for you, team, right? And now we come into state C. State C is at 6 volts, like I said. When this latch is confirmed, that is when this is the vehicle part, right? So this is done by the vehicle. This is dependent on the vehicle manufacturer and his criterions. So when the vehicle feels that it needs charging, this relay or this switch is latched, and the voltage further drops across R2, and thus the voltage effectively becomes 6 volts. So state A, B, C. These are the primary states that you need to understand. These are the major states that that needs to be understood, right? The other states I'll come into. So as you might see, this is what happens when an electric vehicle is connected to an electric vehicle charging station. It's not just you're connecting electric vehicle, the current is coming, charging. No, you have a clear case of communication. You have a clear case of happening between the electric vehicle, between the charger and the device, with the vehicle, right? So now I mentioned about the duty cycle, right, and how the duty cycle affects or responds in as for the amperage that is available by the the station, right? So basically, when the negotiation happens, when the EV and EVSE negotiation happens, the lower value is considered, right? Whichever is the lower. Like the car proposed that I can charge at this amps, the station proposed that I can give you this much, and the lower of the value is considered at the prime point, right? The lower of the value is divided by the vehicle, right? So as you can see, if your duty cycle is at 10%, right, then your amperage output considered by the vehicle, understood by the vehicle side, is at 6 amp. So basically, if you are giving out on through the signal, on through that 1 kilohertz generator, what you're giving out is that the system is capable of delivering 6 amps only. And thus, when you give out this duty cycle, when you're giving out 10% duty cycle for your system, for your schema, what you effectively tell the vehicle is that you can deliver only 6 amps. And the vehicle understands that, and thus vehicle responds, I'll take only 6 amps. Consider you have a provision to provide 12 amps. What you do is very simple. You change the duty cycle of your existing wave to 20%. Thus, the car understands, or the vehicle understands, that your system is now capable of delivering a higher current or a higher power, and the vehicle could eventually take in higher current. And it could go all the way up to 80 amps at 96%. It's for, at like said, 20 kW system, a 3-phase system, right? So this is how the charging power or the charging current is completely understood, is completely transferred or communicated between the vehicle and the charging station. I hope this is clear. This is the oscilloscope view of how this whole system happens, or how this whole schema happens. See, consider this is the plus or minus 12 volt, right? So if you are trying to do an experiment, I'll recommend that you guys try to do from 0, because getting a plus or minus 12 volt 1 amp power supply, I mean variable square wave, could be a little bit difficult. It's not something that is easily available. Better you can try out between 0 and 12, and I guarantee that putting between 0 and 12, the value between the voltage between 0 and 12 is not going to affect any charging issues. But the only thing that it's going to affect the security of the devices a little bit, because if you don't have the minus 12 volt, then the diode check is obviously not going to do any purpose. So if you are putting your gun in some puddle of water which has some electrical conductivity, or which has a resistance of 2.174, then that's going to be something that's hazardous. That's why you have this plus and minus 12 volt. But for reference purpose, for research purpose, for understanding, for simulating, I hope you could do it with from 0 to 12 volts. Right? So when we consider the first scenario, the 12 volt signal line, but the electric vehicle is not connected. You have this 12 volt signal line that is running straight. It's not, the vehicle is not connected, but at this point the vehicle is connected. And you can see that there is a time delay due to this transition. There is a time delay which we suppose should be there, because the transition is happening from 12 kilowatt, I mean 12 volt DC to 9 volt square wave. So now at this point we have a 12 volt standard DC, and we are having, at this point when the vehicle is connected, state B, EVSE is ready, EV is connected. At this point we have a voltage of 9 volt square wave, and as you can see, the duty cycle is 50%. 50% from our truth table means that it's at 30 amps, right? So when we are putting up 50% duty cycle, the EVSE is advertising, or EVSE is telling the EV, the electric vehicle, that I am capable of delivering 30 amps. You can take up to 30 amps. So whichever is lower is considered by the electric vehicle, right? And when after the EV is connected and EVSE is ready, the voltage further drops to 6 volt when it goes through the 1.13 resistor, right? So now the voltage has dropped to 6 volt. So when the voltage has dropped to 6 volt, what effectively the state says is that it has reached state C, which is indicative of the EV is ready to charge, the EVSE is ready to give power, and it's charging. The charging is happening, right? Now at this point, the charging has been completed, or the charging has been stopped, but the EV is still connected. That's why we have the 9 volt square wave. And at this point, the plug is removed, EV is removed, and that's why we have the 12 volt straight line. And this part, the whole process is repeated, right? So this is how it would look on an oscilloscope. or on a simulation, or on a UART, if you're taking it on a UART and representing it over MATLAB or something, then this is what it would look like, right? Proximity, like I said, I'm not going to go deep into the proximity schema, but I'll give you a little bit glimpse into it. Everything that is happening in proximity in the EV charger is through resistor networks, is through voltage comparators, and is through voltage drops across the multiple resistor networks that are present in the EVs and EV charger. Everything is a resistor game. Everything is voltage drops. You're measuring the voltage drop. You're comparing multiple voltages. You're dropping voltages across networks of resistors. So basically, the proximity pin, the proximity pin, what does is that it identifies the stages or schemas where the vehicles are connected or not. Right now, the proximity is not of very importance, because the proximity, earlier the proximity pin or the proximity criterion has to be taken care of by the board or by the central control system. Now what we do is we do the whole proximity control schema within the gun itself, within the connector point itself, so that it's taken care of very early. The voltage division, all you have to know is basic standard electrical things like the voltage division across resistors, how the voltage is divided across resistors when resistors are connected across different networks. This is what you have to understand across when you're understanding the proximity sensors, right? So what generally happens is that these proximity systems have switches, right? So these switches are responsible for having the whole system controlled, right? I'll take you to the previous schema. On the fifth pin, if you're identifying on the fifth pin, you can see the proximity. You can see the proximity line that is running across the vehicle and across the EVSE connector. And this proximity pin actually identifies the voltage drops and understands whether the vehicle has been connected or not. But there is another feature that proximity does. It's through S3 or a switch or a physical switch that gives a command or gives a state signal such that the user, that makes the EV understand that the user wants to plug out the electric vehicle. Why S3 is present? Because I said you're handling high amount of power. You're handling 7 kilowatt. You don't want to unplug your vehicle without stopping the discharge. It could destroy. It could it could lead to the rapid closing. It could lead to rapid opening of controllers. It could of the relays, of the contactors, which is not advisable, which is not something that a commercial product would be having, right? So S3 or the switch here allows graceful start and stop. So you have to press the switch. Pressing the switch will drop the voltages across the line and will make the vehicle understand that the user wants to pull out the charging station or pull out the charging plug, right? So that's what the graceful start and stop is about. So when you press the S3, there could be hello. Am I audible? Do we have any?
Yes, you are audible, Ramanunni. You are audible.
Yes. Hello.
Yes, Ramanunni, you are audible.
All right. So there was an echo coming back. That's why.
No, that was some noise from other participants.
All right. So, like I said, the proximity pin, the proximity point is added for safety, and there is another aspect is the switch. It's a physical switch that helps you pull the plug without destroying any of the physical components. And the reality is that the solid state components in the vehicle side will be able to shut down the power almost to zero instantaneously than the physical mechanical components. Right? The relays, the mechanical components, obviously they need to close in or open up during a specific time, right? But the solid state components, they are able to bring down the whole power to a standstill before you are trying to remove the plug from the vehicle, which is much more safer, which is much more advisable for EV chargers, right? So this is basic resistance and voltage division and total resistance calculation across that network that I've shown you just before. I'll send you the the presentation or the file, the presentation, so that you could, if required, you can have this taken up from you. But it's just basic electrical engineering. All you need to do, what are the resistors that are coming out at each point. You need to understand which are the voltages that are being divided. You need to compare these voltages, understand the stages. Stages, like I said, it all happens in stages. You need to understand the stages. Like I said, if the button is, see, if it's not connected, the voltage on the proximity, if in the simplest sense, if it's not connected, the voltage would be 4.5 volts. If the button is pressed, the voltage would be reduced to 3.0 volts. If it's connected, the voltage on the proximity pin would be 1.5 volts. And how you understand that, how you achieve through, how you understand the voltages or how you compare the voltages is through the drops that are happening between the resistor networks, right? So you have got three stages. One, when it's not connected, the voltage should be close to 4.5 volts. When it's connected, when the button is pressed, when the S3 button is pressed, the voltage on the pin would be 3.0 volt, but it has to be connected. When it's connected and the button is not pressed, it will be 1.5 volts. Three stages, right? So right now, in the design that I have shown you, in the design that I have just described you, it's a poor quality design, right? It's not something like the design that I have shown you. This one. This is a very basic design. This does not take into multiple factors that needs to be considered. But this I just took in for that. I just thought that it could be a little more easy to understand. Right? So that's why I took this picture. But the major reasons that pertains or that exists in the development or in the R&D of type 2 device or communicative charging devices is, one thing is incompatibility of multiple devices. Like the type 2 devices need to be connected to the type 2 cars. Safety features are something that are important. In India, you might know we don't have any chips that are being produced by us, so we do have a dependency of outsourcing, right? So, and as you might know, the components, the quality of components, everything that is dependent on cost, and that could lead to overheating or any other issues that could be there, right? So these are the challenges that we might face while we are trying to design a charging station, right, sir? Now you have understood the major basic part of how a charging station communicates, how a charging station controls, how a charging station is connected, and how a charging station and a vehicle speaks. So basically, you have the knowledge, you have the complete understanding to make a charging station or a charging environment from your side based on the J1772 system, right? So before we go into the next session, I think, sir, can we have 5 minutes off? Trinu, sir?
Yes, Ramanunni?
Can we have a 5 minutes break?
Yeah, sure.
Thank you.
We will have a short break of 5 to 10 minutes and we will resume by 10:15. As Ramanunni is having some power outage issues, so he is trying some other alternative to get his laptop charged. So he has confirmed that he will be back in another 5 to 10 minutes. I wish to tell all the participants one thing. We will start our afternoon session. Afternoon session, we will start at 2 o'clock. At 2 o'clock, we will have the validatory function. Followed by that, we will have a group photo session. Group photo session is nothing. All the participants are requested to turn on their camera for a while, so that I will be taking the screenshot, which is required for making the report, which I have to send to Adal ACT Academy. Then by 2:15 or 2:20, we will start the exam, the assessment, and the assessment will be of 30 minutes. So all the participants must be present at 2 p.m. without fail. Around 2:15 to 2:20, we will start the assessment session. And there will not be any separate attendance link for the third session of the day. Those participants who are taking the exam, from there, we will be taking your attendance. So you don't have to worry about the session 3's attendance today. Dr. Yudhishthir Pandey sir, the first session's attendance link will be shared only after the session, sir.
Okay, sir. Okay.
The last day of the program.
Okay, sir. Okay.
The same information to Prashant Mali ma'am, Prashant Mali sir also. Another information which I wish to share with you is all the participants must give your feedback in ADAL portal. There are in fact, three conditions for you to get your certificate. The first condition is 80% attendance. Second condition is 60% mark for your assessment. And the third condition is a feedback from your end must be provided in the ADAL portal. Usually what happens is like many of the participants after 2 days of the FDP, we'll be continuously contacting the coordinator saying that you haven't received your certificate yet. So in majority of the cases, the major reason behind that will be the participant might not have given their feedback in the Aadhaar link. You don't have to give any feedback. We haven't circulated any Google form to submit your feedback. You have to go yourselves into the Aadhaar portal as a participant login, and you have to give the feedback about the session without fail. Then only the certificate will be issued to you. So all of you must make sure that you have given your feedback submission soon after the program. If everything goes fine, that you have taken your exam and you have scored more than 60% for your assessment, and you have more than 80% or you have more than 80% for your assessment. And the third condition, if you had given this feedback, then definitely the certificate will be automatically generated by Aadhaar portal to you. Someone is asking to repeat about the assessment process. Okay, by 2 o'clock today, we will be starting the third session. Third session is actually the validatory session. It will be around 10 to 15 minutes. During that period itself, we will take a group photo also. At that time, I request all the participants to turn on your camera so that I can take the screenshots too, which is required for the submission of FDP report in Aadhaar portal. In the Aadhaar portal, you will be able to get the feedback link only after the completion of this FDP. That is only after 4 p.m. today, I guess, or by tomorrow or day after tomorrow, the feedback link will be updated in the Aadhaar portal. So you have to wait till then.
No, it's already available, sir.
It's already, but in the last 2 sessions, yesterday while evening when I was checking, it was not there.
Now it is visible.
Okay, fine. If it's okay, thank you, ma'am, for your great information. So Vijay Lakshmi ma'am has shared with us that it's already available because some of the participants are asking for the link. So if it's already available, means definitely you can start giving your feedback now itself, no issues. And regarding the assessment,
Sir,
yes, tell me. Yeah, and regarding the assessment will consist of 20 questions, and the duration for the assessment is of 30 minutes. Mostly we will start the exam by soon after the validatory function, so that many of the participants has requested me that they want to leave early today because some Ganesh Chaturthi function they are having, or they all are busy with some Ganesh Chaturthi festival at their states. So we will try to start the exam by 2:10, 2:15 itself. So soon after the exam will be of just 30 minutes. If you are completing before that, you can leave early. So you can submit your exam, and I will try to make a provision so that you'll be able to take the exam anytime between 2 to 4. Once after you have started the exam, only 30 minutes will be there for you to complete the exam. And the exam will consist of 20 questions. 60% is required for getting the certificate. 60% means you have to get 12 answers, or you have to get your 12 questions correct. That's all. Hope Ramanunni is back. We can continue with the session. Ramanunni? Ramanunni, are you available? Just a sec.
Yes, sir. Sorry, I was on mute.
It's okay, Ramanunni.
Yeah.
So shall we continue?
Yeah, we shall continue. We shall continue. I shall share the screen back.
Yeah.
Yes. So we are back in the discussion with chargers, right? So right now we are at the point where we have the basic knowledge of and understanding on how charging schema works, or how the charging protocol, or how the J1772 specific schema works on between electric vehicles and the electric vehicle charging stations, right? So now we move into a little bit more understanding, a little bit more modern concept on charging, right? The smart charging. I also on the last presentation, on the last class itself, I gave a little bit more importance or stress on smart charging, because smart charging is like the fruit of it, right? So like I said, it could be an interim solution that could be very helpful for grids, that could be very helpful for distribution companies, that would be very helpful for power companies in managing the grid constraints, in setting and calculating the prices based on the time of the day, based on the peaking, based on the usage, based on the availability, considering and constraining charges based on the requirement of the users, and as well as integrating renewable microgrids, or local renewable systems that are available within your premise or within the reach of the charging station into a single entity, so that the whole ecosystem is more green, is more feasible, is more power adjustable, and power efficient, energy efficient, right? So that's what smart charging is about. So basically, ChargeMOD, we have our own smart charging algorithm. We have our own smart charging schema, which we call AmbiCharge. The AmbiCharge schema actually follows a distributed and dynamic load management system. Previously, I told you how the pulse width modulation, how the duty cycle of a system determines the maximum power is available for multiple systems. I think now you are understanding how AmbiCharge is able to distribute the load evenly and maintain load constraints. We, in turn, dynamically control the duty cycle. That's what we do through Smart Genie. I'm giving you the hint. Controlling the duty cycle dynamically lets you control the amperage output dynamically. Simple as that. In the simplest terms, see, it's a whole channel, it's a whole pathway that we need to design, that we need to bring in. But in the simplest term, that's the thing. Right. So dynamically, remotely, if you're able to control, if you're able to intelligently control the load, the duty cycle, based on some existing schema, based on some existing machine learning algorithm, or a schema that you have developed, based on your existing usage, based on your existing user cycle, everything that needs to come into consideration. And there is another thing that it needs to consider. It is the grid constraint, right? Right now, in most parts of India, we do not have a smart grid setup. We do not have grids that have a communication enabled between them. We are having this shift very soon. We will be having, I think, every single discom is looking towards IoT-ifying their devices, right? Internet, connecting their devices to the internet. I think smart charging and smart systems should be something that is of huge research importance, right? So a smart charging schema gives you a very flexible atmosphere, a very flexible charging atmosphere, so that you could deploy multiple systems, multiple charging units with lesser load constraints. That's what you can do. That's a huge thing when you're considering a charging point operator. When you're able to reduce the loads, when you're able to reduce the demand charges. See, the more load you take, the more costly it is. The more load you take, the more monthly recurrent cost it is. The more load you take, the more capital investment it is. It's obviously more profitable to any charging point operator. It's any business that is running in the energy segment, energy sales segment, or energy transaction segment. It's very important that it needs to be monitored. It needs to be flexible. It needs to be smart, and it needs to be adjustable based on our requirement, right? So that's what the whole smart charging ecosystem is about, right? So, like I said, you can have local renewable integration. You can have the smart charging programmed in such a way that most of the usage happens from your existing PV, and you take the lesser availability from the available grid. And you can set it in such a way that when peak happens in the grid, charging constraint mostly happens through the solar, right? Or when you have a dip in the grid, you don't take energy from the solar. Instead, you take it from the grid, right? So that you keep the grid in a stable position, right? So that's what the integration of existing microgrids or mini grids, or even your virtual power plants into the solar, into the charging environment can do. And then the thing is coordinated charging. Like I said, if you have multiple devices deployed across your premise and you have load constraint. See, consider you have a shopping mall. They have 10 devices deployed, but they have a load of only 30 kilowatt. But the total load requirement is 70 kilowatt. What shall they do? What's the output for them would be a coordinated charging schema in which each of the chargers are connected, and whenever charging schedules are happening, the dynamic load balancing would happen so that only the available load is distributed among the parked cars or the charging cars, right? And like I said, peak management is one of the important aspects of smart charging. You have to understand, you have to get real-time grid statistics, you have to get real-time grid values to connect, communicate, and essentially coordinate with the peaks. Now, the end point of our session would come to with Open Charge Point Protocol. So OCPP, I've given a very good hint on OCPP, the importance of OCPP, what OCPP does in the charging station environment during the last session. So basically, the OCA, based out of Netherlands, they were formed in 2014. But OCPP, the protocol, actually was developed way back. So, like you see from the presentation, OCPP was actually devised during 2009, and the first viable version is OCPP 1.2. It was the first viable public version. As in being an open charge protocol, as in being an open protocol, you don't require a licensing fee, you don't require a registration fee, you don't require a subscription fee. You are free to use OCPP like that, right? That's what the beauty of open comes in. That's where the beauty of open comes in, right? So, and in 2015, OCPP 1.6 was published. OCPP 1.6 is kind of like the most utilized OCPP version ever. It's like the Windows XP, right? So OCPP, see, Windows XP is still being used across computers around the world, right? So that's what OCPP 1.6 is about. OCPP 1.6 is the Windows XP. It is going to be around for a longer time because it just is compatible. It just is compatible with almost everything. So it's the Windows XP of charging stations, right? So and in 2018 we have the newest confirmed public version, the 2.0. It was published, and in 2020 you had the 2.0.1, which was the OCPP 2.0 version. When it was launched in 2018, it had multiple smart charging considerations within it. So basically, the 2.0 version, the prime mentality of the developers or prime mentality of contributors towards OCA towards OCPP 2.0 was towards smart charging. And in 2020, and I think now in 2021, there is a higher version available, like 2.1.2 or something, that is available for OCPP. So Open Charge Alliance, like I said, they're responsible for the whole ecosystem, right? So this is how it would look. This is the whole diagrammatic representation of how an EV charging endpoint software ecosystem would look like. See, for the customer, it all begins with an application. All he needs to know is turn on the application, connect the charger, turn it on, get the billing done, right? So basically, there is a load happening in between. There is a load happening inside of the servers that enables the whole infrastructure to work seamlessly. First thing is very simple. The OCPP schema, which is used to communicate between the CMS and the charging station, right? So basically the charging station and the CMS, both of them should be OCPP compliant so that they could talk via OCPP. And CMS, which is the central management system, which is the back-end office system of all the collection of functions that we need for an application to function, right? It could be specific, it could be customized, it could be tailor-made as per our specific server requirement, our specific requirement of our business model, right? It is dependent. But the OCPP library is something that turns in or stands in as unilateral. It doesn't change, right? Now, Open Charge Point Protocol, like I said, it's maintained by Open Charge Alliance, which has headquarters in Netherlands, and the major functionality is maintaining or enabling interoperability between chargers and the charge point operators or the charging station networks. It's one of the simple representation on how these things communicate, right? So you can see the electric vehicle is getting charged. It is just getting connected to the electric vehicle charging station. The charging station is getting power from the electric grid, and the charging station is communicating to the CSMS or the CMS, which are both the same. And that could be the endpoint, or the CMS could further communicate to an app point or a web portal or something like that, so that you could control the endpoint charging station activity from the user device, right? So open source is something that is interesting for we or people who are interested in the research area, people who are working on in the research area. But unlike that, OCPP is something that is huge commercially, huge in the industry, huge in the market, because there is no current alternative that is as viable as OCPP. So even though OCPP being the open primary protocol for networks charging stations, you don't have much viable. There are alternatives there because we have our own protocol. ChargeMOD has ChargeMOD charge control protocol, which is different from OCPP, but it just doesn't work, right? Because we have our protocol based on our requirements, based on our systems, based on our schemas, and it's based on some other communication method, right? So it just doesn't work. So OCPP is something that is there, standardized, so that there is an interoperability between the chargers. Like I said, how ATMs would work. See, consider the scene where ATMs, State Bank of India ATM would only accept State Bank of India card. That's not something that's acceptable, right? So interoperability is something that you need to be very sure about, and OCPP brings in that to a greater extent. And OCPP actually controls and manages big aspects, huge aspects around the charging environment. First thing, the authorization, the identification of the user through the application. It's done by the application, and then from that, the authorization of charging, accessing the charging station is done through the application through OCPP. The remote modification of charging, charger configuration, the voltage, the amperage, maximum outputs, the real-time updates, the over-the-air updates, all things are made impossible through OCPP. The real-time status values of charging stations. What is the current condition of charging station? What is the current fault value of that charging station? See, you could have different faults, right? So you have a current specific fault, you have that fault code or error code, you have that getting transmitted, so you understand what is the error at that charging station remotely. Smart charging, like I said, reservation of charging, that is also a part of the normal user authorization. So this is a standard set of cases that OCPP brings in, right? The 1.6, which is the median version, you can look at that. That should be the most commonly used version. So basically, it's available in two versions, the JSON format and the SOAP format, but JSON being the most easy to use and transportable format, lightweight. So JSON is, I think, most in use. And there is also a .py version, but I don't think that is in circulation for a greater extent. JSON is something that is being used. And smart charging is supported, but up to specific load constraints or specific use case scenarios only, like load balancing and charge profiles. Those are the only things that were supported in OCPP 1.6. But later, when it came to OCPP 2.0, multiple, and 2.0.1, various smart charging schemas, like the ISO 15118, the smart charging schema, was added. The smart charging functionalities that was included in OCPP 2.0 was carried forward to 2.0.1. These are the aspects that is currently in trend with Open Charge Point Protocol. It might not be very interesting, but I guarantee you this protocol is something that we are going to hear every day sometime in the future. So basically, the Open Charge Point Protocol allows the communication between the charger and the CMS. And before that, like we saw, a power line communication enables the communication between the vehicle and the charger. Right? So now you have a holistic idea of how the whole communication happens. Now you understand that how the communication happens between a vehicle and a charging station. You know that. You know the stage machines. You know how each stages represent each different current values. You know how a vehicle communicates with the electric vehicle charging station. You know that. And now we have a basic understanding of how an electric vehicle charging station communicates to the cloud or the central management system, CMS or CSMS, right? Simple as that. So this is the whole ecosystem. You have, I think from this session, you should be having a very basic understanding of how the whole ecosystem is connected, how the whole ecosystem communicates between one another in a seamless way. Now, I'll let you understand. Let you into a little bit. What shall I say? Like I said, ChargeMOD has its own charge point protocol. So we enable that through MQTT. MQTT is a lightweight messaging platform, lightweight message transmitting method. So we use MQTT and we have our own custom method that we use for charging. Why do we use that? Is because for some specific chargers, for example, for the two-wheeler and three-wheeler chargers, OCPP is overkill. You don't need OCPP, or implementing OCPP on the device side and server side could be costlier. So that's why we developed something called the ChargeMOD Data Transfer Protocol, CDTP. That's how it's called. So CDTP, ChargeMOD Data Transfer Protocol, is much more lighter, much more easily transferable, and the frequency of data could be easy to maintain for us. Right. So that's why we came up with an alternative to an open global schema. But that's not an alternative. That's just a fork of what it existingly is, I'd say. So that's our MQTT server, ChargeMOD's MQTT server. So basically, ChargeMOD has got two servers that are connected to a single user interface schema. One is based on MQTT, which connects to our own devices, and the other one is OCPP, which connects to generic devices. Right. I think this could be the case with most of the charge point operators. So like I said, the MQTT server, MQTT, I think most of you must be familiar with MQTT. MQTT is like a common data transfer protocol. Basically, like if it's lightweight, Mosquito, it's commonly known as Mosquito in the broker side. Yep. So this is how the CMS would look like. So the CMS is, like I said, the CSMS, or the charge central management system, or CSMS, central charging station management system. So this is how it would look like on a first time. It's our screen, it's ChargeMOD's schema. So you can control and have an understanding of everything that is going around with all the charging stations that are installed under you in one single point. You can get the data from any charging station. You can push data to any charging station. You can push updates over the air through over-the-air updates from this point. You can understand, deactivate, activate any charging station, users, payments, everything that has been defined is predefined in and directed through the endpoint, which is the dashboard, right? And now we come into the application interface, which is very prime in the endpoint, because see, you have done everything in the perfect way, but your app is not good, then it's not going to work, right? So with ChargeMOD, we have a very user-friendly app, a very tangible, in terms of usage. So you can just tap, you can download the application. ChargeMOD app is available in the Play Store, in the Apple Store as well. You can just download the application. You can see all the charging stations nearby you. You can just go to a charging station, scan the QR, start your charging facility. You can scan a QR and charge to the driver who is currently in charge. There are many things that you can do with the ChargeMOD app. I mean, in fact, everything that a user would require or a driver would require in an app, I think we have facilitated most of the facilities inside the ChargeMOD application. So I'll show you a little bit glimpse on how the ChargeMOD app works. Just give me a sec. I'll show you a hint on using the application. Right. Yep. So that was a simple video of how a two-wheeler is being charged using the application. Go to a station, use the application, scan the QR, and charge your vehicle. simple as that. That's how we have defined the whole system. Now, everything that we have heard from the very beginning to the end, everything culminates in the application, right? So that's what we have done. And that's what ChargeMOD has been doing for like in the past 2.5 years in terms of the development environment. So any questions? I think I should be taking that from now on. Thank you.
Yes, thank you, Ramanunni. And now I request participants to ask your queries to Ramanunni M.
Hello.
Yes, sir. Yes, sir.
Yeah. Good morning, sir. Again, a wonderful session. I enjoyed a lot, and in fact, I got the very nice information from sir again. Sir, I just have a point like, is it possible to guide our undergraduate students regarding making one project on maybe EV charging or electrical vehicles, maybe solar or hybrid or like the EV charging stations? Is it possible for you? Or some sort of help from your side?
Yes, good morning, Gatke, sir. So basically, I shall be, I mean, from my perspective, I would be able to help you in terms of charging station design, charging station research and development. I might be able to do that. And in terms of specific electronic components and specific mechanical design of electric vehicles, also, I might be of help. I might not be of importance there, I guarantee you that, but I could be able to be of some kind of help. I could be able.
Okay, fine. So regarding that, shall I send one mail? Not like exact help I needed from your side. As per your schedule and as per your as per your busy schedule, you can just give guidance to the students so that they will be benefited from you. Like I am getting benefits from your side. No, that's why I wanted to have the benefits to the students also. So please help in that so that they also can get nurtured, no? And in fact, as I saw you, like your age is almost 30, 35, not more than that.
Sir, you are mistaken, Gadge, sir. He is just a 2018 pass out. So he's
2018.
25 or 26.
25. Wow, very nice, sir. In fact, you should help our students, sir, because accordingly, you know, the students get nurtured and that way also, no, they can become the entrepreneurs also. And today's scenario, it needs it. So yeah, fine. So I'll just mail. I do have your email ID, so accordingly, I'll just mail. Okay. Thank you so much, sir. Thank you so much.
Yes, thank you, Gadge, sir. Any other queries from participant side?
Hello, sir.
Yes, sir.
My name is Nitin Jogale from Amravati. I'd like to share with Gadge, sir, who is from Nagpur College. Sir, we make a project on electric vehicle also in 2015 batch, which is assisted with solar panel.
Okay, sir.
We are from mechanical branch, so you can contact with Borakadi sir, so that they are our guide.
Okay, fine.
Okay.
Okay.
Thank you.
Very nice session, sir.
Thank you, Nitin, sir. Thank you.
Yes.
Yes, sir. Shanavas, sir. Shanavas, sir, are you available? Shanavas, sir. Shanavas, sir, is not available. Now I request Divyanath ma'am to step forward and give a feedback. At least any one of the participants, please step forward and give your feedback for this session to Ramanunni. All are writing in the chat messages that it's a very good explanation, sir. Nice session, sir.
Hello?
Yes.
Hello?
Yes.
Hi, Ramanunni.
Yes, Lakshmi ma'am.
Hi, Ramanunni. I'm Lakshmi Nair. Our teacher would be happy if his students will get placed in some high positions or PSUs or get placed from the college, etc. And his happiness will be double or triple when he was an entrepreneur, actually. So in that respect, you have done a great job, and I'm happy of you that you have started at a very young age. You have started a startup and working hard on that. Thank you for the informative session, and also all the best for your future endeavors. And also your presentation was also very good, and even your presentation slides are interesting. Okay, thank you all altogether. A very big thank you, and all the best to you.
Thank you, Lakshmi.
Thank you very much, ma'am. I mean, I'm thankful for the opportunity. Definitely. Thank you.
Yeah. Ramanunni, that was another amazing technical know-how session from your end. Just like what the participants are responding, even many are responding in the chat messages, you will be able to see that very clearly. In fact, I will say that I am very proud of you, because just like one of the participants has told that you're just at the age of this 25, you have started a startup, and it's quite established now, and KSEB Limited and all are one of your clients. So it's really a great thing that you have achieved in this short span of time. Really proud of you, Ramanunni. The major, I can feel from your session that the major driving force for you to have such a great success in this short span of time is your passion. So always keep your passion up, Ramanunni, and thank you for being with us. And we expect you to be with us for the upcoming sessions also, for the upcoming FDP programs also. Okay, Ramanunni?
Hopefully, sir. Hopefully. Thank you.
Okay, Ramanunni. Thank you. Bye.
Thank you, sir. Thank you. Thank you all.
Bye bye.
I will be sharing with you the attendance link now. Just a minute.